Hello everyone, welcome back to Spectrum classes. In my previous video, I have discussed about the molecular orbital diagrams of carbon, nitrogen and beryllium, boron, etc. And now we are moving towards the molecular orbital diagrams of oxygen as well as fluorine. But before going to oxygen and fluorine, I must tell you there is a difference between the molecular orbital diagram of nitrogen and molecular orbital diagram of oxygen. So what is the difference? I have highlighted here. So rest is same, but only the difference is in the bonding molecular orbitals which are formed by the overlapping of p atomic orbitals. Can you tell me which one is for oxygen and which one is for nitrogen? Let me show you. This is for oxygen and fluorine, and this is for nitrogen and the diatomic molecules which are having less atomic number than the nitrogen molecule. So here you can see lithium, beryllium, boron, carbon and nitrogen. We are going to draw in this manner. First pi molecular orbitals and then sigma molecular orbital, and these two are bonding molecular orbital. However, in case of antibonding molecular orbitals, we follow the same path pi star and then sigma star in both the cases, right? Here you can see pi star and sigma star. So the difference is only for the bonding molecular orbitals of the molecular orbitals which are formed by the overlapping of p atomic orbitals, right? So here is the difference. Now a question comes to my mind again and again, and several times my students have also asked why this difference occurs. Sometimes we may confuse that we are having the correct order for up to nitrogen and then there is a change in the energy order of the oxygen. No, actually this is not the correct way. Correct way is this. So first we must have sigma and then pi. But here is the exception for boron, carbon and nitrogen case. Now the electronic configuration. So here I have written the electronic configuration. Since we should follow this order only, and here I have written the electronic configuration in the increasing order of energy. So here you are having sigma, sigma star, then sigma 2s, sigma star 2s, then sigma 2p, either x or z, whatever you consider on the internuclear axis. So that will be there. And now the pi. So this arrangement we should follow. But up to nitrogen, we are not following this order. We are reverse this order of bonding molecular orbitals which are formed by the overlapping of p orbitals. Now the question comes why? Why we are doing this? So here I am going to show you why we are doing this. So this is up to oxygen and this is up to nitrogen. And why we are doing this? The reason behind this is the mixing of orbitals. So what is that mixing of orbitals and why it occurs? So here, before describe this mixing of orbitals, I must tell you the energy difference between 2s and 2p atomic orbitals. So these are the atoms, and for these atoms, here is the difference in the energy between the s and p orbitals, which is mentioned here in kilojoules per mole. So here you can see I have also highlighted this with the red circle that the energy difference is this much, right? And for oxygen and fluorine, we are having very high energy difference between the 2s and 2p atomic orbitals, right? So for these oxygen and fluorine, the mixing of orbitals doesn't take place. However, in case of boron, carbon and nitrogen, this mixing of orbitals of 2s and 2p atomic orbitals takes place. So what is that and how it occurs? That I am going to explain you here. So normally we are following this order. So here by the overlapping of 2s we are getting this sigma 2s, and here we are having sigma 2s star. Here is the sigma 2p x, and here are pi and pi, and here is again our pi star, and now we are having sigma star. So this is the order which we need to follow, but up to nitrogen we are not following this order. So this sigma 2s and this 2p forms the sigma orbital. By this kind of overlapping, it forms sigma orbital, and this is forming sigma orbital like this. So px px and this 2s 2s, the energy difference is less, as I shown you in the table. So these two atomic orbitals, due to less difference in their energy and almost same symmetry, they are combined together, or they are mixed together to form hybridized molecular orbitals. So what are these hybridized orbitals? So initially we are having this order: sigma, sigma star, sigma, and then sigma star. I'm going to highlight here also. So here is this, and this. These four molecular orbitals I have shown here. Pi orbitals first and then sigma orbital in case of bonding molecular orbital. Whereas, so after mixing, the 2s atomic orbitals going down in their energy, whereas the sigma 2pz and sigma star 2pz are going high in their energy, right? Whereas the pi orbitals remains at their same places, right? So that is why up to nitrogen we are following. After this nitrogen, we are having the order similar to this, right? So the mixing of orbitals of 2s and 2p is the only reason why we are following this exception up to the nitrogen case. Here you may have a question, what is this psi 1 and psi 2? If you are a class 12 student, you can skip this part. And if you are a student of B.Sc or M.Sc, then you can understand this part through quantum mechanics. So here psi 1 stands for mixing of sigma 2s plus sigma 2p. Whereas this psi plus 2 stands for, this is the linear combination of these atomic orbitals. So sometime I will tell you hybridization in valence bond theory. So psi plus 2 gives you by the linear combination of sigma star 2s and sigma star 2s, that is antibonding orbitals of 2s and 2p orbitals. Now coming to the psi minus 1. So what is that psi minus 1? So if we are having, instead of plus sign, we are having minus sign, then here psi and this psi 2 minus star. So we are having minus. So minus are antibondings. I explained it in molecular orbital theory in the first lecture. So here these are of high energy and probability of finding the electron is less as compared to the plus. So here we are having psi minus and psi minus 2. So this again I am going to explain here. So suppose we are having this 2s, right? And after mixing we are getting this sp orbital. So this s and this p mixed together, therefore it is somewhat increased in energy, right? So here you are having sp orbital, that is hybridized orbital after mixing, and which is of slightly higher in energy. Similarly on the right hand side. Similarly, if we are considering that the p orbital and the s orbital mix together, they again form sp2. Why this sp1 and sp2? The designation is just because two atomic orbitals combined, they will form two hybridized orbital, right? Similarly, two atomic orbitals combined, they will form two molecular orbitals. Two orbitals mix, one s and p, right? So we will get 2sp, two atomic orbitals. So sp and sp orbital, hybridized orbitals we will have, right? So here this is just the designation 1 and 2, that is sp and sp. One hybridized orbital is this, second hybridized orbital is this. So that is why I have written over here. Now since this p orbital mixed with s orbital, therefore it is of low energy. Here you can see, right? In both the cases it is of low energy and it is of high energy. So that is the reason why I have drawn here. Now coming to the next. When this sp atomic orbital, these are now hybridized atomic orbitals which combine together and they will form two molecular orbitals. So here you can see So if I ask you what kind of difference you are finding out from here to here, this is just theoretical explanation. Otherwise, it is given quantum mechanically, right? So just to avoid the complications, I am just explaining it in a simple words, right? So here what you have seen that the atomic orbitals, and here are the molecular orbitals, bonding and antibonding. And if we see the energy difference between the bonding molecular orbitals and antibonding molecular orbitals with respect to the atomic orbitals, that the energy difference is same. However, that is not the case here. You can see here. So the energy difference is different here in this case, right? If we consider this p orbital, then we are having this kind of situation. So by overlapping of sp orbitals, these four are of almost same energy and of same symmetry. Therefore, by mixing of four hybridized orbitals, we are getting the four molecular orbitals. Now, what about these pi orbitals? So pi orbitals we are having at the same point where they were previously. So this is how you can understand up to nitrogen, because the energy difference between the 2s and 2p atomic orbitals is less. Therefore, mixing of 2s and 2p atomic orbitals to form hybridized orbital which are having different energies as compared to the normal which we expected, right? So that is the reason behind that up to nitrogen we are having pi orbitals are at low energy as compared to the sigma molecular orbital, whereas after the nitrogen molecule we are having our pi orbitals of high energy than the sigma atomic orbital, right?